Greetings, ladies and gentlemen. This is your boy Kamal once again, and he's back after, a 3-day absence, I guess. I'm terribly sorry about that. But I'm back with a very, very awesome integral. This is an absolute banger. We have the integral from 0 to pi by 2 of x squared divided by 1 plus sine x plus cosine x. And the solution development is really beautiful. It's quite elegant, and the final result is just beautiful as well. I mean, it's going to be very satisfying. So how exactly do we begin the solution development? Well, I have sine x and 1 plus cosine x in the denominator. So what if I expand them using the half-angle formulae? By that token, we have the integral from 0 to pi by 2 of x squared divided by sine x is expanded as 2 sine x cosine x by 2, of course. And 1 plus cosine x would be expanded as 2 times the squared cosine of x by 2. Now from here, we can factor out 2 cosine x by 2. And the reason I want to do that will become clear in a short while. We have 1/2 the integral from 0 to pi by 2 of x squared divided by... Okay, so we factored out cosine x by 2 and the factor of 2. So that means we're left with tangent of x by 2 here, plus 1, which is pretty cool, and we have cosine square x by 2, integration with respect to x. Now, of course, that means we have integral 0 to pi by 2 of x squared times 1/2 of secant square x by 2 divided by 1 plus the tangent of x by 2. And now we have a suitable structure for integration by parts, because notice that we have the function in the denominator, that's 1 plus tangent of x by 2, and its derivative would be 1/2 of secant square x by 2. So that means we have the integral from 0 to pi by 2 of x squared d log of 1 plus tangent x by 2. And all that's left now is to perform integration by parts. So that means we have x squared times log 1 plus tangent x by 2, with the limits being 0 and pi by 2, minus integral 0 to pi by 2, derivative of x squared is 2x. So we have 2x times log 1 plus tangent x by 2 dx. The limits are pretty straightforward. As x approaches pi by 4, we have tangent of x by 2. No, wait, as x approaches pi by 2, we have tangent of x by 2 approaching tangent pi by 4, which is, of course, 1. So that means for the upper limit, we have pi squared by 4 times the logarithm of 2 minus, as x approaches 0, of course, we get a 0 term, minus twice the integral from 0 to pi by 2 of x times log 1 plus tangent x by 2 dx. And we'll call this integral I sub 1 and shift our focus to this one. Actually, you know what? Before we get to I sub 1, let's make the obvious transformation here. That is letting x by 2 here equal to u, which implies that dx equals 2 times du. So that makes it the integral from 0 to pi by 4 of 2u. So we have 2 out here. U log 1 plus tangent of u, and we have 2 times du as well. So that means we have a factor of 4 outside. And this means that the target integral I is actually pi squared, terribly sorry about that, pi squared by 4 times log 2. Again, terribly sorry about that. Watch out for the timestamps for terribly sorry about that and okay, cool in the comment section. Thank you very much for that. Minus 8 times the integral from 0 to pi by 4 of what exactly do we have? We have log 1 plus tangent of u du, and I might as well not call this I sub 1 and just rename it without the factor, the one integral after the transformation. What am I trying to say? I'm trying to say that this integral here is I sub 1. Why is math so much easier than talking? Interesting. So we have I sub 1. That's the integral from 0 to pi by 4 of u times log 1 plus tangent u du. And to evaluate this bad boy, we're going to expand the tangent function here so that we have integral 0 to pi by 4 u times log 1 plus sine u divided by cosine u du. On simplification, we have integral 0 to pi by 4 u times log cosine u plus sine u. And you know what? Using the properties of the logarithm, we can write this as a difference of logarithms. So we have this minus log cosine u term as well. Now distributing the multiplication here, we have integral 0 to pi by 4 u times log sine u plus cosine u minus integral 0 to pi by 4, terribly sorry about that again, of u times log cosine u du. And I forgot the differential element over here. Anyway, so what on earth am I supposed to do with these two integrals? Well, they look quite different, but they're not too different. They're a bit similar, rather quite similar. Let me show you what I'm talking about. We have the sine u plus cosine u term here. This could be written as root 2 times sine u divided by root 2 plus cosine u divided by root 2. Now, why have I introduced these 1 over root 2 terms? Well, we know that 1 by root 2 is, in fact, the sine of pi by 4 as well as the cosine of pi by 4. And the other integral has a cosine term, so I might as well write this as the cosine of one thing minus another thing. So I have root 2 of sine pi by 4 times sine u plus cosine pi by 4 times cosine u. So that means this can be compressed into root 2 cosine of pi by 4 minus u, which is pretty cool. And this implies that the integral I sub 1 equals integral 0 to pi by 4 u times log of root 2 times cosine of pi by 4 minus u minus the integral from 0 to pi by 4 of u times log cosine u. Okay, cool. And again, making use of the properties of the logarithm, we can separate the root 2 from the cosine term so that we have integral 0 to pi by 4 u times log root 2 plus integral 0 to pi by 4 u times log cosine pi by 4 minus u minus integral 0 to pi by 4 u times log cosine u. And everything's looking good so far. First up, we have 1/2 of log 2 times u squared by 2 on integration, limits being 0 and pi by 4. Now, what on earth do I do with the other integral? Well, I could introduce the phase shift, that is taking u from the u realm to the pi by 4 minus u realm, which means I have the integral from 0 to pi by 4. And if this is sort of unclear, it should not be unclear, especially if you're watching this video. I mean, if it wasn't clear, I think you would have friends to hang out with. Comment F to pay respects. Anyway, so we have this phase shift. If this is not clear, again, you can just perform a u substitution or a t substitution, letting t equal to pi by 4 minus u. Something called King's property. Well, it's not King's property. I mean, I have never read the term King's property in any literature on math or calculus in particular. I've never read the term. Why is it famous as King's rule? I do not know where that thing came from. This is just a property of the definite integral by virtue of its symmetry. It basically means integrating from left to right is the same thing as integrating from right to left, as in adding those areas left to right is the same thing as adding those areas right to left. A reverse parameterization, calling it reverse parameterization would be a bit cooler, I guess. A lot cooler, in fact. Anyway, so we have this phase shift giving us pi by 4, terribly sorry about that again, pi by 4 minus u times log of pi by 4 minus, here we have pi by 4 plus u now, correct? Yep, that's it. We have some cancellation taking place. And of course, we have this other integral being integral 0 to pi by 4 u times log cosine u. And that means we have a quarter of log 2. Pi squared by 4, pi by 4 squared would be pi squared by 16. Everything's looking good so far. Plus we have pi by 4 times integral 0 to pi by 4 of log cosine u minus we have integral 0 to pi by 4 of u times log cosine u. And look, there's another one of those. So that means we have twice that integral. And now, just let me write this as I squared by 64 times log 2 plus pi by 4 times another integral that I'm going to call I sub 3. And 2 times this integral I'm going to call I sub 1. I sub 2. Why not name this one I sub 3 and 2 in the particular order in which you see them in the previous step? Well, I want to evaluate this integral first. So here we go. Now for solving I sub 2, I'm going to make use of one of my most beloved tools, and that's the infinite series expansion for log cosine. So we have log cosine x. We might as well rename the dummy variable to x. It doesn't matter anyway. Log cosine x equals negative log 2 plus the sum over the non-negative integers. No, wait, it's the sum over the positive integers k of negative 1 to the k plus 1 times the cosine of 2kx divided by k, which is absolutely beautiful, no doubt. Link in the description for a proof. There are 2 proofs, in fact. Well, there's one proof. One is in video form on YouTube. The other is on Instagram in form of a write-up. Anyway, so how exactly are we supposed to make use of this infinite series? Well, all I have to do is expand by u and integrate from 0 to pi by 4. That seems pretty straightforward. So we have negative log 2 times integral 0 to pi by 4 u du. I swear these log 2 terms are everywhere. Plus, I'm switching up all the operators now. We have the sum over k of negative 1 to the k plus 1 divided by k times the integral now from 0 to pi by 4 of u times cosine 2k. I renamed the dummy variable without even knowing it. What do I do now? I seem to be overthinking things. Do I go back and rename it to x? Or would that look like fumbling up? I'm overthinking this. I say I stick with the name of the u variable. Like, why not? So I have u times cosine 2ku. Now to evaluate this integral, which we need integration by parts for, I'm going to call this I sub k, because we have the sum over k anyway, so it looks nice, I guess. di, we're differentiating u, integrating cosine 2ku, 1, 0, sine of 2ku divided by 2k. Then we have a negative cosine. Terribly sorry about that. Negative cosine 2ku divided by 4k squared. Alternating plus and minus signs. And here's one term, here's the other term. Everything's looking good so far. So that means I sub k equals u times the sine of 2ku divided by 2k. Limits being 0 and pi by 4. Then we have a positive sign, and we have cosine 2ku divided by 4k squared, limits being 0 and pi by 4. So plugging in evaluating the limits, that is, for the upper limit, we have pi by 8k times the sine of k times pi by 2. And for the 0 limit, we get a 0. Plus, now we have 1 by 4k squared, and we have cosine of k pi by 2 minus 1, which is looking pretty damn neat. That's I sub k. And don't forget what we needed. We needed the sum. That looked awful. The sum over k of negative 1 to the k plus 1 divided by k times I sub k. So distributing the multiplication and summation over all terms, what we get is in fact pi by 8 times the sum over k of negative 1 to the k plus 1 times sine of k pi by 2 divided by k times k, giving me k squared, plus a quarter of the sum over k again, of this time negative 1 to the k plus 1 times cosine k pi by 2 divided by k cubed now. And we have a minus sign, a quarter, sum over, terribly sorry about that. Oh, wait, I mean the sum over k. I think we can name an index, terribly sorry about that as well, but that would be a bit cumbersome for writing. Now we have negative 1 to the k plus 1 divided by k cubed. Okay, cool. So far so good, but now we need some further analysis for the index variable k over here. Notice that for the first sum over here, the sine sum, we have for k equal to 2n, where n is a positive integer, sine of k pi by 2 being equal to sine of n pi, which is, of course, 0. And similarly, for the cosine term, we have cosine k pi by 2 equal to 0 whenever k here equals 2n minus 1, where again n is an integer, a positive integer that is. Okay, cool. So let's just discard all of those terms then. And this implies that this thing here that I'm going to call S for some reason. So the sum here equals pi by 8 times the sum over the positive integers n now of -1 to k plus 1 turns into 2n minus 1 plus 1. Cancellation. So you have -1 to the 2n, which is, of course, equal to 1. Then we have sine of 2n minus 1 times pi by 2 divided by k squared is now 2n minus 1 squared minus, no wait, it's a plus sign, plus a quarter of the sum over the positive integers n again of -1 to, again, k plus 1 will turn into 2n, which is, of course, -1 to the 2n is 1. So we have cosine of, no, wait, terribly sorry about that. We have -1 to the k being equal to 2n now, because for the odd values of k, the terms in the sum vanish. So we have 2n minus 1 here, which is, of course, equal to -1. So that means we have negative sign outside. And now for the sum, we have cosine 2n times pi by 2, which is, of course, cosine n pi divided by 2n cubed. Okay, cool. And finally, we also had the sum here, which is a quarter of the Dirichlet eta function evaluated at 3. So we have a quarter of eta 3. Now, what about sine of 2n minus 1 pi by 2? Sine of 2n minus 1 times pi by 2 equals -1 to the n minus 1. Yeah, that's about right. And then we have for cosine n times pi, we have -1 to the n. Yep, that's correct as well. So this implies that the sum S here equals pi by 8 times the sum over n of -1 to the n minus 1 divided by 2n, terribly sorry about that, 2n minus 1 squared, minus a quarter of the sum over n of -1 to the n, again divided by 8n cubed. So we have 32 here, n cubed there. And notice that if we pop back in this negative sign as a n plus 1, or equivalently an n minus 1 term for -1 to that power, then again we have the Dirichlet eta function. So this thing here is 1 by 32 times eta 3. And we already have a quarter of eta 3. Subtract those two, then you get what exactly? I'm not very good at math. I'm just guessing that this here equals -7 by 32. So we have pi by 8 times a very important constant. That is, of course, the original top G, Catalan's constant. So we have Catalan's constant minus 7 by 32 times eta 3. Okay, cool. And of course, we can express this in terms of Apéry's constant, that's zeta 3, by using the functional relationship between the eta and zeta functions. So we have pi by 8 g minus 7 by 32 times 1 minus 2 to the 1 minus the argument, that's 3, times zeta 3. So you have 1 minus a quarter, that's 3/4. So you have pi by 8 g minus 21 by 4 times 32, just guessing, 128 times zeta 3, which is a beautiful result for the integral I sub 2. Wait, no, that is not the result for the integral I sub 2. That is, in fact, the result for the sum S. You know, that sum over the integrals. Where exactly was it? Yeah, that's the result for the sum S. But for the integral I sub 2, I have to scroll all the way back up to here. So to the result of that sum s, we have to add the result of this integral, which is, of course, equal to pi squared by 32, right? U squared by 2, yeah, perfectly fine. Negative sign, then we have log 2 over here. So that means all I have to do is just add this term here. So we have the integral I sub 2 equal to negative pi squared by 32 times log 2 plus pi by 8 g minus 21 by 128 zeta 3. Okay, cool. And of course, the result for I sub 3 can be derived using exactly the same procedure. All you have to do is integrate the log cosine u series. Okay, and now it's time to piece everything together to get the result of I sub 1. I sub 1 equaled pi squared by 64 times log 2 plus pi by 4 times log 3. So that means you have a negative pi squared by 16 log 2. And you have plus pi by 8 times Catalan's constant minus 2 times I sub 2. So that means plus sign here, pi squared by 16 log 2, some nice cancellation straight away, minus pi by 4 times Catalan's constant, and you have a negative sign, so now it's a plus sign, plus 21 by 64 times zeta 3. Okay, that's a pretty striking result, no doubt about that. And here you had 21 by 64 zeta 3, and piecing it together gives us pi squared by 64 times log 2, and you have plus pi by 8 times g minus pi by 4 times g, so that's going to be negative pi by 8 times Catalan's constant, and you have 21 by 64 times Apéry's constant, which is a pretty beautiful result in itself. But what about the target integral? Well, the target integral I had this pi squared by 4 times log 2 minus 8 times I sub 1. So that means we have pi squared by 4 times log 2 minus 8 times the integral. So we have negative pi squared by 8 times log 2 and plus pi times Catalan's constant minus 21 by 8 times Apéry's constant, and pi squared by 4 minus pi squared by 8 would be pi squared by 8. So that means the final result for the target integral I is pi squared by 8, terribly sorry about that, times log 2 plus pi times Catalan's constant minus 21 by 8 times Apéry's constant, which is an absolutely ridiculous result for a very cool integral. I hope you enjoyed the video. Most importantly, I hope you learned something from the video. Be sure to like and subscribe. Do drop me a follow on Instagram. And in case you learned something and you're learning something from the channel, you believe I'm doing a good job, consider supporting my content on Patreon. Thank you. See you next time.